And of course, you can remember that anytime we talk about rate of flow, you can remember that anytime we're talking about rate of flow of something, because we said it's the rate of flow of electric charge. Anytime we talk about rate of flow, we're talking about that parameter is being studied based on the influence of change in time. Are you getting me now? So when we say that current is the rate of flow of electric charge, we are saying that it is charge flowing with time taken. So that means I, which is current, is equals to rate of flow of electric charge. So that is the expression. I equals to Q over T, where Q is your what? Your charge. These are your basic knowledge you know. T is given as your time. And if I may ask, your charge is measured in what? Your charge is measured in what? Quickly tell me. What's your charge measured in? I is what? Current. And our current is measured in what? Of course, we know this is measured in seconds. Charge is measured in what? Your charge is measured in coulombs. Measured in coulombs. So it's measured in coulombs. C. That's what we call C. Measured in coulombs. While your current is measured in ampere. A. Are you getting that now? Why it's measured in ampere, which is what? A. Okay. So these are the basic first knowledge you must have under this idea, because we are actually going to be talking about a lot of things in this class. We're going to be extending the lecture, talking about we're going deeper into your potentiometer, your Wheatstone bridge, and some other stuff. You get now? So that's that for that. That's that for that. Okay now. Okay. We can actually explore this better. With desire, you're not all right. We can actually explore this better, and we'll be going deeper to talk about some other concepts. Now, this formula here is what results in your normal formula you used to see when you be seeing Q. You're seeing them right, Q is equals to what? I T. That's from this cross multiplication. You understand? From this cross multiplication, when this cross multiplies IT and Q, so they are having quantity of charge is equals to what? IT. You understand? So that's that knowledge for that knowledge. Are you getting me now? So if I may write a question on the board, there's a prepared question we have here, and the question says, calculate, let me erase this. I believe we've written what's here. We have written what's here, right? I can write this question down. The question says, calculate the quantity of charge. That's our first problem for the night. I'm just solving only one problem for this aspect because this is basic knowledge. Calculate the quantity of charge. Calculate the quantity of charge flowing through a conductor. That will be the question. Flowing through a conductor, if a current of 10, if a current of 10 amps passes through the conductor for 10 seconds, passes through the conductor for 10 seconds. Now, let me just rotate this a bit so we can see what we have there. Okay, so this is what we said. We said calculate the quantity of charge flowing through a conductor if a current of 10 amps passes through the conductor for 10 seconds. Are you getting me now? If the current of 10 amps passes through the conductor for 10 seconds. Are we together, please? Are we following? Are we following? Okay. Now, how do we solve this kind of question? Let's be very serious here. Hope you guys are solving and you are prepared. The first thing first to do, we can easily say that write out your parameters. By writing out that parameters, you can see that based on the question, calculate the quantity of charge. So what we're looking for is the quantity of charge, which is Q. We don't know what Q is, and we're trying to find what Q is. So find the quantity of charge Q flowing through a conductor in a current of 10 amps. So our current I has been given to us as 10 amps. Are you getting me now? Passes through the conductor for 10 seconds, and that means we're saying our time is equals to 10 seconds. That's we're moving at a very fast pace. So these are the parameters that were given to us, and we're going to be using these parameters to solve this problem. And based on these parameters given, Q, we have Q, quantity of charge, we have I, which is our current, and we have T, which is our what? Time. So we can easily make use of the formula we wrote previously, which is Q is equals to I T. Very straightforward, very simple, but stay at the beginning, please. These are basic knowledge you have to know if you don't want to have problem with this concept of this topic. And that means we're saying equals to, current is 10, so we're saying 10 times, and our time is 10. 10, and that gives us 100. So, very important to put your unit. So, our quantity of charge for current of 10 amp flowing for 10 seconds is going to be 100 coulombs. So, you can quickly take note of this. Quickly, you can write that down because we want to go to the next concept, which is Ohm's law. Are we together? Are we done writing it? Please, if you are done writing it, just signify it on the comment section that you are done so that I can move on to the next concept. It's very, very simple. This is the beginning part. And trust me, we have a lot of things to do. A lot. Okay, Jessica, you're done. Yuri, you're done. Chubumi, Desire. Okay, we can move on. So that means we can move to the next concept, and the next concept is about Ohm's law. You can be told to state Ohm's law. In fact, it is in the past question, 2014, they told you to state Ohm's law. And trust me, many people, you omit a lot of things by stating that very simple law, and I will be helping you with that. Ohm's law. Now, Ohm's law just says that the current flowing through a metallic conductor is directly proportional to the potential difference across the terminals, given that temperature and other physical properties remains constant. Now, you have to actually take note of keywords there is the fact that we're talking about a conductor. Some people just say the current is directly proportional to the potential difference, which is very wrong. You have to specify that we're talking about the conductor, because remember we were able to state and postulate that current also flows in semiconductors when the temperature has been increased. True of us, we talked about that when we're dealing with semiconductors, their bands and stuff like that, valence band, electron band. But now we are specifying that it is conductors that Ohm's law works for. When a current I flows through a metallic conductor, you understand? I say that current is directly proportional to the potential difference across the terminals of that conductor. Are you getting me now? So, saying that I was saying, the current I flowing through a conductor is directly proportional to the what? Potential difference. Directly proportional to the potential difference, e.g., across its terminal, given that temperature and other physical factors remains constant. So that's what the law is actually stating. You get that now? Now, basically, to remember these laws sometimes might be kind of stressful for the brain. You get, so I used to advise people, if you want to actually remember this law, 003. As you can see, desire, you ask the question, what? Look up, 003. You get it? Now, we proceed. Now, factors remains constant. Now, if you want to remember this law, just remember this mathematical expression that your V is proportional to I. Of course, this is the same as saying I varies directly as V or is directly proportional to V, which is what the law is stating. True or false? True. Okay, so we can bring in our constant, which is R. You know the R is going to be a constant. Since your R is a constant that affects the current flowing through it, because resistance is the opposition to the flow of current. So that means every metallic conductor is going to possess its own resistance. I get me? I'm going to possess its own resistance, and that's what we call R. I get me? So R is our resistance to the current in that metallic conductor. So if you are bringing in a constant, we're going to bring in the constant at the R side, at this side, and our constant is going to be like the resistance. So we can just be saying the Ohm's equation, that is Ohm's law, the Ohm's equation. The Ohm's equation is what? V equals to what? I R. We know that V is what? Potential difference measured in volts. And we also know that your I is your current measured in ampere, and your R is resistance. And I told you the meaning of resistance, the opposition to the flow of current. R is resistance measured, I said measured in R, measured in ohms. Okay, so you can write that down, and we'll just solve one question from that aspect. Please, are we together? Are you done writing this so that I can erase this and move to the next aspect? I don't want to take the camera far away so that I can picture the whole body. Yes, I can do that. I can take far away, picture the whole body. But the problem is, it will not be like you won't be able to see the write-offs properly. So if you are done, please just inform me so I can wipe off this. Let's be sharp, let's be sharp, let's be sharp, let's be sharp. Okay, Zaya, you're done. I'll wait for 3 or 4 other people to be done before I move on. Once just solve question from this, then we'll go to arrangement of resistors, both the ones in series and in parallel. And you know another thing I can tell you guys, if you know that I'm about to wipe this off and you're not yet done, you can actually get a screenshot of the board. Like you can get a screenshot, get a screenshot is it seems, then maybe later on you can write it down if you skip it. Please, you understand, to make work faster. I get me now. These of you that wanted classes by 10, this is part of the disadvantage. I can see data network. I don't know how your network is right there, but we have no choice to manage it. Okay, so are we done? Can I wipe it off now? Can I wipe it off? Okay, so let's just solve one question from this first, from this Ohm's law we just did, before we move on to the next aspect. And this question says, or better still, before we solve the question, let's talk about, let's just talk about arrangement of resistors. So I will do that because we'll be applying this concept Ohm's law in our resistance arrangements to obtain our resistors and stuff like that. You get? So let's just do that. Okay. For those of you that are just joining, don't worry, I'll still save the video. You get the previous contents that we have already. You get? So now, We can arrange resistors in two ways. We are talking about resistors arrangement, and we know that that can be done either series or your parallel. Either you do it series or in parallel. And the truth about the matter is that so many people do not understand the concept of resistors in series and in parallel. You must have been misinformed by certain kind of individuals that resistors in series are is an arrangement that's just in a straight line, and that's not true. Okay, it's not about straight line or bent line or curved lines. You get, it's about there being a repeated end-to-end connection of those. You get, it's just about there being an end-to-end connection between each resistor. You connect one resistor and you connect the resistor to another resistor directly without there being any internodal junctions. You get. So let's just move straight and just talk about series. Resistors in series. Resistors in series. Resistors in series. Now look at this. When you have something like this, I'm using this to represent my resistors. You can also use, you can either use this to, you can use this symbol to represent your resistor. Are you getting me now? That's your resistance, or you use this. Any of them works. Both of them are for resistance. Okay. So I'm using this now. Now, if you look at this diagram, you'll be able to appreciate and see that we have an end-to-end arrangement. From R1, you get the first beginning of R1, we connected it directly to the end of R1, directly to the end of R2. Are you getting me now? To the beginning of R2, sorry. Then from the end of R2, we connected another wire. All these lines represent wire to the beginning of R3. I see now. That's why I said in a series connection, we have an end-to-end what? Connection of the resistors. You get. So this is a series connection because it's end-to-end connection. You get this one from the end of this one, go to the beginning of the first one, from the end of this one to the beginning of the first one. And as you can see, these are the terminals of this diagram now. Are you getting me now? Good. There are things you must take note of when you are talking about resistors in series. There are things you must take note of when you are talking about resistors in series. Now, we have to know how the current flows in a series connection, how the voltage are produced, the potential difference are induced in a series connection also. And we're going to be talking about that now. Now, in a series connection, listen up. In a series connection, when the current I is flowing through this, as you can see, there is not going to be any obstruction in this current flow. So this current is not going to go from here, move to R1, going to pass from R1. The same current will pass through R2. Then this same current will pass through R3. It means that what? In a series connection, the current is the same. The current that passes through all the resistors are the same. I get what I'm saying now. So we can just write it down. In series connection, the current through each resistor, the current I through each resistor is equal. Are we getting that? The current I through each resistor is equal. That means the current here is equal to the current here, equal to the current here, and that is I. So I, which is the current flowing through, we flow through R1, and that's the current we flow through R2, and that's the current we flow through R3. Because in some question they'll tell you find the current in R3. The current in R3 is the total current flowing through it for series connection. Are you getting what I'm saying? Okay. Now, but your voltage is not constant. That means what we're trying to say from this question is that current is constant through this. But your voltage is not constant. Your voltage is not constant. Are you getting me? Your voltage will be dependent, are you getting me now, on the value of your what? Of your resistance. Are you getting me? Yes, yes. They are the same thing. They are the same thing. Yes, we said in series connection, the current I through each resistor is equal. Are you getting me now? That means they are the same. They are the same. Are you getting me now? The current in R1 is the same current in R2, the same current in R3. You get no cause for alarm. Now let's now go to the second thing about series connection. The voltage is not the same. Oh. Don't think the voltage are the same. The voltage are not the same. The voltage is dependent on the value of your resistors. That is the value of the resistance. The voltage is dependent on the value of the resistance in each resistor. Do you know why it is not dependent on the current? Why the voltage in each of them is not dependent on the current? Since the current is the same, that means the current cannot alter the value. Remember the formula for your V is what? Remember that the formula, recall that V is equal to IR. I get it now. That means the V in this place, what you? The V in this place, to compare the total V across this kind of, circuit, series connection with what? What you? That means we'll be having total V, which is our total voltage, will be equal to what? Will be equal to the voltage in this R, in this one, we call it V1, plus the voltage in this along this resistance 2, we call it V2, plus the voltage flowing across R3, which we call it V3. I get me. Follow me. This thing is very important and very simple. So this is the voltage flowing through all of them. Actually. Now remember we said V is equal to IR. It means IR total. This is going to be the total current. Since this is the total voltage, R2 is standing as the total resistance, and I is the current. Remember we said the current is the same that is flowing through each. So IR is equal to be IR1. That the voltage in V1 in R1 will be what? Current flowing through times the resistance. Since we said the formula for voltage is this. You get it? So we say IR equals to IR1 plus the one in V2 plus IR2 plus IR3. I get me now. So that means V here is the one that is IR1. The V here is what? IR2. The V here is what? IR3. But the total V, that this one we call V1, V2, V3. So the total V is what we wrote here, V1 plus V2 plus V3. In case you are asked to calculate the total voltage flow, this one and this one. Okay, who can tell me what I'm going to do next? What is common in all of them? I and B. As you can see, our I is common because it's the same current that is flowing through all of them. So I can just come here and say I RT is equals to I is common into brackets R1 plus R2 plus R3. Let me show you how I did this. We factorized. If you don't understand, just drop your question. We factorized. I is common in all of them. So we brought out the I, open bracket, divide IR1 by I, you be left with R1. Divide IR2 by I, you be left with R2. Divide IR3 by I, you be left with R3. I get what I'm saying now. You get left with R3. Okay, so when you do that now, you now be having this I here can cancel this I here, and that's what makes us have RT equals to R1 plus R2 plus R3. So in a series arrangement, of resistors, our R is our total resistance. In a series arrangement of resistors, our total resistance in this place, which we call the effective resistance. I can write it here, where RT is the effective resistance. Where RT is the effective resistance. Are you getting me now? Or you can call it the total resistance in that circuit. So for series connection, this is what you have. Please let's write it down quickly. Now we move to the next one. Please, if you are done, let's signify that we are done so that I can erase. If you are done, let's signify. Okay. If you are done, please let's signify quickly. I'm waiting for you guys to finish writing. Okay, I believe we're all done. Okay, yeah, I mean the majority of us are done, so I can move on. I can move on to the next one. So I want to go to resistors in parallel. We just finished shooting resistors in series, so I'm going to resistors in parallel now. Remember, in series, the end of one connects to the end of the other, the end of the other connects to the beginning of the one, then the end of that one connects. So there is just is linear. I get me now. So it means listen, oh, it means that even if they draw something like this, if they draw a resistance like this for you, these two resistors, these three resistors R1, R2, R3, are they in series or in parallel? These three, are they in series or in parallel? They are in what? They are in series. Not because people used to tell misinformed students and make them feel that okay, when these two like this will be in parallel, these two are not in parallel. They are in series. All of them are in series with each other. Why? Because it follows the same procedure I told you. The beginning of one goes to the end of the other. The end of the other goes to the beginning of the other one, and it continues like that. So if you look at this R1, I mean R1, this is the end of R1, it gets directly connected to R2. This is just like bending your wire. It's still straight. It's just like bending the wire. I get him now. It's just like bending the wire. So it's still straight. So this is connected in series with R2. And R2, this is the end of R2. R2 was not connected again directly to R3. So that is still series connection. I just want to clear you guys and your understand, open your mind to it. Okay now. So let's go to parallel connection. Let's go to source connection. So resistors in parallel. Resistors in parallel. Resistors in parallel. Now, remember in our series connection, we have we connected it straight. And I told you not just about straight, it's about the linear connection of these resistors, whereby the end of one connects to the beginning of the other, and that sequence continues in that format. That's what I said. Now, the same thing still applies. A different thing applies now in parallel. In parallel connection, what you're going to be having is all the resistors are going to connect to a single junction. They're not going to be connected to each other. They don't have any direct connection with each other. I get it now. There will be a common node. What I call the node is the point where all the wires are intersecting. I get it now. Where wires coming from different resistors or different cells, but now that we're doing resistors, they intersect. I get it now. That's what we call a node or a junction. You get, or a junction. So there will be a junction that's going to be, they're going to serve as a point of extension of these resistors. So it will now be the point where we are rearranging, those resistors. So it's just about you having different resistors connected to a single junction, and that's when you see they're parallel. So look at this. If I should have something like this, but you can see this resistor now, I now connect this resistor. Okay, this is another resistor here. Let me just draw it first. So these are three resistors: R1, R2, R3. If I now connect all of them, look at this one here, this one here, this one here, this one here. And now connect all of them to a common junction. This is the node. I see this point here, this is a junction. Because as you can see, all the resistance and resistors were connected to that point. I get me now. All resistors were connected to that point. Same thing maybe here again. Maybe here again. So please, it's not about cramming the diagram, it's about understanding the reason why the diagrams were like that. Understanding the reason why the diagrams were like that. Now, this is it. We are connecting R1, R2, R3 to a particular junction. They did not connect to each other. It's not like I connected this one to this one and connected this one to this one. No. I get me now. Remember in series, the end of one will go to the beginning of the new resistor. Then the end of that resistor, you have another wire going to the beginning of a new resistor. But here we're not having that. What we're just having is each resistor connecting to the junctions. Are you getting me now? That are present in them. So what do we now see? What can we now use to postulate this? We can now use or bring out from this that was, if you have a current, follow this rule. If you have a current, I, and this current is flowing through, the moment that current gets to this junction, something is going to happen. The moment the current gets to that junction, it's going to divide. They are going to split. They are going to proportionalize. They're going to, should I use the word, differentiate themselves based on those regions that are present. So this current I here, that is flowing, I get it now. It will be flowing. When you get to this junction, of course, it cannot be partial. The current cannot be partial. Are you getting me now? Desire, you have wahala. The current cannot be partial. So some of the current will flow upwards like this. Listen, though, some of the current will go like this, they will flow upwards to this R1, and that's what we call I1. Some of the current just go to serve R2, and that's what we call the current that passes through I2. So if this current that passes through I1, this one is going to pass through R2. Then some of them, the remaining portion now will now go to and serve I3, and that's what we call it I3. So these arrows are telling you the direction of the currents. Those arrows are showing you the direction in which those currents are flowing. I get what I'm saying now. Now we have been able to appreciate, we have been able to explore the directions of the current that until they get to this junction. Are you getting me now? And that's when you'll be having this current getting differentiated based on the fact that they are trying to cross over different resistors present. And this happens only in what? In parallel connection, because only in parallel connection that you'll be having this sort of junction right here that will cause this current differentiation. So now, what can we establish? What facts can we establish? What facts can we state from this diagram? From here, remember in our series connection, if I may ask, in our series connection, is current constant or which of them is constant, current or voltage in our series connection? Is current constant or voltage constant? Which one is constant, please? You can remind me. In our series connection, is current constant or voltage constant? Which one is constant? Quickly, okay? With constant sense, that's very correct. You guys are following me, that's it. So Shubomi, very, very correct. Your current is constant, but yeah, as you can see, it's no. Who said voltage? Voltage is not constant in series. Someone just said voltage. Voltage is not constant in series. Are you getting me now? Voltage is different, and we said the sum of each voltage in each resistor is equal to the total voltage. I showed you already. Are you getting me now? It is your current that's constant for series. But right here, as you can see, our current is not constant. Our current was flowing, and the one that flowed through R1 is different from the one that flowed through R2, and different from the one that flowed through R3. And that's what brought about I1, I2, R3. Jessica, very good. So we have, you can say from here that, remember, in series connection, current is constant, but in parallel connection, it is voltage that is constant. So you write there, voltage across each resistor, voltage across each resistors are equal. Sorry. According to each resistor, I use the word each resistor is equal. So the voltage here is equal to the voltage here and equal to the voltage here. It's not like V1, V2, V3 because they are equal. We call it V. The voltage here is V, the one here is V, the one here is V. Are we together, please? Now, the second thing we now say is, do we remember? We can recall that I is equal to V over R. True or false? Because we know that V is equal to IR. So if we make I the subject of formula, we have V over what? Over R. True or false? True or false? True. Okay. Now, we can now establish the fact that in a series and parallel connection, the total current, I total, the total current flowing through a parallel connection, I get me now, is actually equals to the sum of all the currents, meaning our I total, which is this I here that was flowing, the total current that flowing, is equals to I1 plus I2 plus what? I3. I get me now? And we've been able to appreciate the fact that what I is equals to V over R. I get it now. So we can establish that phenomenon or this demonstration right here in this expression. So we'll be having I C equals to our I1 will become, we can't write V1 over R1 because we said V is constant. So we say V over R1. Since the voltage flowing through all of them are the same, we just say V over R1. But for this I2, we say V over what? R2. Then for the next one, V over R3. Are we following now? Are we following? Okay, what is common? What should I do now? We have our V to be what? To be common, abi? And if I should come to this place here, this I total, I can write this I total here as what? V all over R total. And what's common in all of them here is V. True or false? So I can say V over RT is equals to V into bracket. Since V is common, I say V into bracket 1 over R1 plus 1 over R2 plus 1 over R3 because we factorize V out of here. I get it. So V divided by this, V will cancel V, that will be 1 over R1. This divided by V, V will cancel V, 1 over R2. I get it. So this V here cannot cancel this V here. We're left with 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This sequence continues this way. And that's how to get the total resistance in a parallel connection. So write it down. Write it down. I believe it is clear. I believe it is clear. This is no where I want to specialize on today. But I say let me just touch it because of God is good. You can understand. These are the basic ideas that you need. These are the basic ideas that you need. What immediately after this now, I will go to solve. We just solve maybe 2 questions. One that will pertain to a combination of both series and parallel. But the 2 of them will be related to that. We solve 2 questions. Then once after the 2 questions, we'll go to another aspect under this current electricity, which will be factors affecting the whether it's resistivity and conductivity. So if you are done, just inform me you are done so that I can wipe off what we have here quickly. And I told you can take a screenshot of it so you can write it down. So please be fast. Are we done? Are we done? Okay, so we're done. I can wipe off. Want to just solve some questions? I can see your prepared past question. Now we have this question, they show a diagram for us here. It said an electrical circuit an electrical circuit is connected as shown, is connected as shown below. Is connected as shown below. Okay. What is the value of the current? What is the value of the current? Is the value of the current flowing through the circuit. And they do the diagram is like this. Very on the diagram. If we are able to deal with this question, it means we understand the arrangement rules. And here was given to us as 12 volts, while here was given to us as 1 ohms. This place here was given to us as 3 ohms. This one here was given to us as 3 ohms. This one here was given to us as 3 ohms. And this one here was given to us as 3 ohms. Now, if I may ask you guys, looking at this diagram, this is the question, I want to solve it. Looking at this diagram now, we have different resistors arranged. The problem is, can we actually identify which one is our series connection and which is our parallel connection? Are you getting me now? That's what one of the major problems is going to be. And how can we be able to identify that? How can we identify that? We have to follow our rules. Now, I'm going to use something to represent it. I'm going to be saying and represent each of them as X, Y, Z, MP, something. I want you guys to tell me which of the resistors are in series, which of the resistors are in parallel. Are you getting me now? Which of the ones are in series, which ones are in parallel. Are you getting what I'm saying now? That's what I want you to tell me. So I'll be labeling it now, and I want you to just comment on it here. Tell me which ones are in series, which one are in parallel. For example, you can tell me SQ is in series or PQ is in series, and then you tell me RQ is in parallel with SQ. And so that's what I want to hear. So then let's imagine maybe this one is X, this one is Y, this one is Z, this one is M. So which one are you going to think are in series? And which one are you going to think are in parallel? This is a GPEP question, and this is the only question I'm going to solve from this aspect because we have a wide aspect to do. Although as time goes on, we're going to be solving more questions. We have drill classes for drilling where we'll be solving questions, variety of questions. And this is the only question I'm going to solve now that will be exploring the fact about connections. Okay, so quickly, everybody start dropping your comment below. Which one is in series? Okay, someone said XZ in series. Let me see. Very correct, Jessica. That's good of you. XZ is in series actually. Yes. What else can we deduce? XYM. Desire, you are saying rubbish. Please, off your phone. Off your phone. How can you say XYM is in series? How? Y and M are in series. Very correct. I don't know who is that, who is using that C8. I think this is enough also. Very correct. Very correct. Y and M are in series. That means Y and M are in series. Jessica, that's good too. Very beautiful. I like how you guys are getting the concept right. As a physics student, an intelligent physics student, the first thing you have to check is where are the nodes? Where are the nodes? So you said so 3 cannot be series at once, Abi? No. Someone asked the question, he said, can 3 be series at once? It can be. You can have 3 things series at once. Look at something. Let me illustrate that. These 3, they are in series at once. These 3 are in series at once. So you can have 3 as series at once. I don't know if they use that to establish a fact. But he said you are drawing is X, Y, M. X and Z are in series. Someone said X and Z. Very correct. Very correct. I don't know who is T, please. Who uses this name at T8? Can just signify so that I can know you. Okay. So we've been able to establish. Look at the reason why. Let me tell you the reason why. The remainder of it I don't understand. We talked about a node or a junction. We talked about a node and a junction. Yes, I'll explain to you this. Look at this point here. This is the first node we have because it's like a T junction. I think it's like a T junction. This is another node here. You can see the T junction. You can see that T junction. Are you getting me now? So I remember I said in series, it's not just about straight. It's about are we having a linear arrangement? Do we have a situation whereby one resistor is connected, the end of one resistor is connected to the beginning through wires? It don't matter if the wire bends or get like this. Did it connect in series? Did the end connect to the beginning of the next resistor without passing through a T junction? Are you getting me? Which is the node, according to Ketchup. You get it? So that's what we're checking. That's really what we're checking. Now, if you check this out, this one here, these 2, they have this direct connection from here, the end of R1 connects to the beginning of Z. But this one here, we cannot say this 2 are in series. Why? Because there is a junction here. You get it? So the first thing you do if you want to answer this kind of question is to reinterpret the diagram into a basic circuit diagram if you are to answer it in your Jupe. Very important to do that. So you will reconstruct it. We said this 2 are in series, this 2 are in series, and we are doing it that these 2 like this, both of them are in parallel with each other. So I can establish that this diagram is this. Where these 2 are X and Z, where these 2 are X and Z, that we said 3 ohms, 3 ohms. Then we now have them connected. I can see this one connected to a junction. So we can just do it like this. You can just do it like this. This is the junction here. I get it now. This one too connected to a junction. You can just do it like this. And this is the junction right here. I get it. So from that junction, what's connected to that junction? Y connected to the X junction side. So we are saying this one are connected like this. I get me, which now connected to M. Also, these are Y and these are M. So this is the junction. I see it. So we have our junction like this. So who can tell me what we notice? We cannot exempt this one here. One is now connected in series to all of them. So this is the one. This is the one which is now connected in series with all of them here. And we now have our 12 volts supplier cell. So that's it. That's it. Are we together? I believe you are getting what I'm saying. Please, hope I'm not lost. I just translated the diagram into this diagram here, into a diagram that is more visible. And I said it's good to do this if you are answering your question. These are complex cell diagrams, arrangement diagrams. I get to be resistor diagrams. So you can actually simplify those diagrams into this, and it makes it more visible for you to work with. Now we can now see these 2 series in parallel. So definitely, if you want to get our current, we know that current, they say find the total current at it. And we know that our formula for current is what? Current is equal to V over R. True of us, we have been given our V. Our V is this 12. The problem is that we don't know our house. Since we are finding total current, we have to use the total voltage over the total resistance. Yeah, so we have to know what the total resistance is, which is our effective resistance. I get what I'm saying now. So we have to know what it is. And how can we do that? How can we do that? It's very simple. We just have to explore. I get it now. We just have to explore these details. And it's very simple. Okay, somebody said no. Okay, let me re-explain. I will explain. Shubami, just calm down. I will re-explain to you now. Look at it. Look at it. This is what is happening. They gave us this. We now want to translate this into a useful circuit diagram. And we said we were able to establish, Shubami, that 3 ohms was connected to what? 3 ohms. And if you look at the way they connected these 3 ohms, look at this, these are junctions. So it is these two that are in series. I get it, and these 2 here in series. But these two, this XZ and YM are in parallel to each other because this is like a junction demarcating them. I get it. The 2 resistors like this, they connected to a junction. So we translated that information into this place. You get it? You don't need to make sure your own is with me the same way it is. You get it? You might decide to use your own line like this, like this, like this. Me, I just decided to do mine like this. In as much as we passing the same information as XZ are in series, YM are in series also, but both of them each are in parallel to each other. I get what I'm saying now. And they are now connected to this 1 ohm supplier here. Are you getting me now? Shubami, are you getting me now? Huh? Please, nobody should be shy, bro. I have your time. Don't be shy. Are you getting me now? Are we getting the concept? Okay, so now we'll be able to do that.